Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about a module, quantization of lattice vibrations under paper solid state physics. So students, let us see what we are going to learn in this module. First, quantize the Hamiltonian of collection of n harmonic oscillator in one dimension. Introduce the quantum mechanical operators satisfying the commutation relation. Third, write expressions for displacement of the jth ion and corresponding momentum. Fourth, know about the energy transported by an elementary excitation of quasi-particle termed as phonon. Write expression for displacement and momentum for ion in 3 dimension. Arrive at the 3-dimensional quantized Hamiltonian. Learn about the lowest vibrational state and its corresponding energy known as the 0-point energy. In module 1, we had discussed lattice vibrations from the point of view of classical mechanics. The agreement between classical and quantum mechanics of harmonic oscillations is very good for high temperatures. But however, as we lower the temperature, the differences between classical and quantum mechanical results increases substantially. That is, what I mean to say is that low temperatures, the quantum behavior becomes more prominent than the classical behavior, and that's the reason why they don't match. A classical mode may have arbitrary amplitude, while a quantum mechanical mode has discrete amplitude. So you understand that if you have studied quantum mechanics, that discreteness is a characteristics of quantum mechanics. The energy of mode K with polarization epsilon K is allowed to have values h cross omega K epsilon K multiplied by n plus half. So here if you notice that this hat operator over this epsilon indicates that it is a vector quantity. And now the frequency omega is not only k dependent, but it is also dependent upon this polarization. There is epsilon, where this index n is more or equal to 0 is an integer. For a single quantum mode of wave number k and polarization epsilon k, n is equal to 1. So what it means is that if you have a single quantum mode, n is equal to 1. If you have 2 quantum modes, you have n equal to 2. 3 quantum modes, n equal to 3, and so on. In the present mode, we will focus on the quantum understanding of lattice vibrations. So look at this figure. You will see that there are 2 potentials which have been plotted. One which is completely parabolic in nature, and that the second one is slightly deviating from the parabolicity. So this parabolic potential is indicating it's a harmonic potential, while this non-parabolic behavior is n-harmonicity. And within these 2 potentials are shown the various energy levels, that these dashed lines, and they are equally spaced with the spacing h cross omega. Thermal vibrations in crystals are thermally excited phonons, and these are just like the thermally excited photons of black body electromagnetic radiation, as you have studied in cavities. The energies of the kth mode with the polarization epsilon k is allowed to have these values, which I again repeat is equal to h cross omega k epsilon n plus half, where n is greater than or equal to 0. So after introducing a little bit about the quantum and the classical difference of lattice vibrations, so let us have a look at this figure where you get to see this harmonic potential and as well as the anharmonic potential. You will notice the difference that the harmonic potential is almost like a parabolic in nature, while in the anharmonic case, the right hand side of this well is not in that exactly a parabolic nature, but it is steep. Now As we had discussed earlier in the previous slide, that harmonicity is an important aspect of these lattice vibrations, because uh, this is an approximation which we already, as I have said, dealt with in the previous module. Now, if you look at this parabolic nature of the harmonic potential, you will see different energy levels has been given. Now, these corresponds to the thermal vibrations in crystals, that is what we are dealing with, and these are thermally excited so-called phonons, or you can simply say the mechanical modes of the lattice, and they are quite similar, or I would say, let us say, analogous to the thermally excited photons of black body electromagnetic radiation in a cavity, which I would assume that you are already familiar with. Now, right in this harmonic potential that you see, the energy levels are discrete in nature. The discreteness, of course, is basically because of the quantum nature of these thermal vibrations. So, what we are going to derive, I'm just telling you right now, the energy of mode K, the vector K, with polarization epsilon K, is allowed to have the following values of energy, that is h cross omega K epsilon K n plus half, where n is more than or equal to 0. So, n here basically represents something like an equilibrium occupation of the thermal vibrations. Now, for example, a single quantum mode of wave number k and polarization epsilon k, n is always equal to 1. And in the present module, actually, we will try to sort of focus on the quantum understanding of these lattice vibrations, which the energies of which are depicted in this particular figure, the harmonic potential figure. Quantization of lattice vibration in one dimension. Now, when dealing with small vibrations in classical mechanics, the Hamiltonian, or a collection of n harmonic oscillators, as in the case of lattice vibrations which we are dealing with, in terms of the normal coordinates pk and qk, can be written like this, that the total Hamiltonian is a summation over these individual k's. That is, take a summation over all the possible k values, and the Hamiltonian of each k is pk into pk star divided by 2m plus half m omega k square qk into qk star. And this is basically a classical result, as we all know. The summation is over all the possible k values, and we know that these k values are dependent upon harmonic oscillators are there. We now quantize the classical Hamiltonian which we had described, and in the process of quantization, what we do is that we replace the dynamical variables qk and pk by their quantum mechanical operators, that is qk hat and pk hat, and both of these satisfy the following commutation relation, that is, the commutator of pk hat and qk prime hat is equal to minus iota h cross delta k prime. When equal to k prime, then this delta function is equal to 1. Hence, after replacing the dynamical variables by their corresponding quantum mechanical operators, the quantum mechanical Hamiltonian then becomes hk is equal to ek hat pk hat dagger divided by 2m plus half m omega k square qk hat into qk hat dagger. So, you see, if you compare this Hamiltonian with the previous classical one, the transformation is very straightforward. That is, we simply replace the classical momentum and position coordinates by their corresponding quantum mechanical operators, and this Hamiltonian is also Hermitian, as you can see. Now, the Hamiltonian HK, the quantum mechanical Hamiltonian, as we had said, is Hermitian, and of course, this is Hermitian also because of the fact that this PK and PK dagger, they are the Hermitian of each other, Hermitian conjugates. Now, taking motivation from the study of quantum mechanics of harmonic oscillator, we introduce the two new operators, AK hat and AK hat dagger, which is defined in the following way. That is, QK hat is equal to this constant, that is the square root of h cross divided by 2m omega k multiplied by AK hat plus A minus K hat dagger, and PK hat is equal to iota times the square root of h cross m omega k divided by 2 multiplied by AK hat dagger minus A minus K hat. Now let us briefly tell you that if you look at this QK and PK, you will notice that they are the sum and difference of these two operators. And these two operators, AK is with an index K and A hat dagger is with an index minus K. So what does it mean? It basically means that when the phonon, the K momentum is annihilated, then a corresponding one with minus K is created. So basically this also is satisfying the momentum conservation. And the operators AK and A minus K dagger, they satisfy the following commutation relation. That is AK A dagger K prime is equal to delta K K prime, as I had mentioned earlier. When K equal to K prime, then this right hand side is equal to 1, otherwise it is 0. And also the commutator of AK and AK prime and AK dagger and AK dagger A prime is also equal to 0. Now, let us go and look at the displacement of the jth ion and its corresponding momentum. So the displacement of the jth ion and its corresponding momentum can be written as delta Rj hat is equal to summation over all the possible k values, the square root of h cross divided by 2m and omega k e raised to power iota k and a multiplied by this ak plus a minus k dagger. And in a similar way, the momentum of the jth ion is written in this way, which is proportional to, that is ak dagger minus a minus k, which is basically it is proportional to the momentum that we had defined earlier, that is pk. So you see the corresponding, that is the position of these ions has a correspondence in the k space. This is very clearly visible. Now note here that the normal coordinates qk and pk and is related to the jth ion displacement, that is delta Rj and its momentum Pj, in the following manner. That is delta Rj is equal to 1 by root n summation over k qk e raised to power I k and a, and Pj is equal to 1 by under root n summation over k pk e raised to power minus I k and a. So using all the results that we have till now discussed, we can now write down the Hamiltonian, our linear chain of ions, as summation over k h cross omega k in the brackets ak hat dagger ak hat plus half. It's quite straightforward to derive this Hamiltonian, and the corresponding eigenvalues and eigenfunctions are written in this way as shown. So as you can see from here, that this Hamiltonian is representing a summation over a large number of harmonic oscillators. This is simply a summation. So each of these ions actually is behaving like a harmonic oscillator, and the entire linear chain is behaving like a summation, summation over all these harmonic oscillators. So the energy of h cross omega k can be associated with the energy transported by elementary excitations or a quasi-particle, which in lattice dynamics is termed as phonons. In the quantum ground state, no phonons are present. That is, the Nj is equal to 0. And on the other hand, the state, the ket vector n1, n2 till nn indicates there are n1 phonons in the oscillator with mode k1, n2 in k2, so on, and n in kn. Okay, so let us now see that what exactly are phonons. Well, just to start with, let me tell you that these packets of sound found present in the lattice as it vibrates, and as the lattice vibrations cannot be heard, unlike static lattice, which deals with average position of atoms in a crystal. Lattice dynamics extends the concept of crystal lattice to an array of atoms with finite masses that are capable of motion. This motion is not random, but is the superposition of vibrations of atoms around their equilibrium sites due to interaction with neighboring atoms. A collective vibration of atoms in the crystal forms a wave of allowed wavelength and amplitude. So, just as light is a wave motion that is considered as composed of particles called photons, we can think of normal modes in a solid as being particle-like. So, in the net result is this, that the quantum of lattice vibration is called the phonon. So, let me put it like this, that you have vibrations in a lattice. These vibrations are of the atoms. These are mechanical modes. You can say that these are mechanical modes. At very low temperatures, then what happens, that they show the quantum behavior, not classical behavior. At high temperatures, they show the classical behavior. So naturally, at low temperatures, when they are showing this quantum behavior, it is more better to talk not of them as mechanical modes but as phonons. So what is basically the difference between phonons and photons that we have just mentioned? So the quantized normal modes of lattice vibrations are phonons. The energies and the momentum of these phonons are quantized. So we can say that it is h nu by lambda. The momentum is simply h by lambda. Exactly in a similar manner is like the quantized normal modes of electromagnetic waves, which are the same photons which we know, and they exactly have the same energy and the momentum, but the energy expression for energy now, because you see that the light is moving at the speed of light, isn't it? Photons are moving at the speed of light, so this energy of this photon would be hc by lambda, and the momentum would be h by lambda, which is the same as that for the phonon. So difference lies in the energy. In one case, we have a phonon, the energy is simply h nu by lambda, where nu is the velocity of that phonon, while on the other hand we have the energy of the photons, which is hc by lambda, where this nu is replaced by c, that is the speed of light. Quantization of lattice vibration in 3 dimension. So now let us discuss and extend our ideas about quantization of lattice vibration in 1 dimension to 3 dimension. So analogous to the 1-dimensional case, we now define 2 new coordinates, q k lambda and p k lambda, and also write down the corresponding operator in the position of the jth ion in the 3-dimensional as delta rj, that is a vector quantity, is equal to 1 by under root of n summation over k n lambda epsilon hat k lambda q k lambda e raised to power I k dot rj0. And in a similar manner, as you can see, that corresponding momentum of the jth ion can be written like is equal to summation over root n summation over vector k lambda epsilon hat k lambda pk lambda into e raised to power minus iota k dot rj0. So here this epsilon hat that you notice is basically the polarization vector, and this polarization vector is introduced because in a 3-dimensional case the polarization is different. 3-dimension, it could be the same also, but it's different. So that is why it is necessary to introduce this polarization, and it is a vector quantity. So the 3-dimensional Hamiltonian then is written like this, that H is equal to a summation over all the hk lambda, that is all the possible allowed values of k, and the summation is not just over k, but now here it is also summation over the lambda. And what is lambda? Lambda is basically the polarization, that is what kind of polarization you have here. The polarization vectors epsilon k lambda, they satisfy the following relations. That is, epsilon hat k lambda is equal to minus of epsilon hat minus k lambda. That is, if you change the direction of the k vector, that is the momentum, immediately you get negative sign in front of that. And epsilon hat k lambda prime is equal to delta lambda prime. Also, summation over j e raised to power iota k minus k prime dot r j0 is equal to n times delta k k prime. Here also let me just recollect that this rj0 is nothing but the position of the jth ion in the equilibrium position, that is without any perturbations, like it is in the ground state, which is undisturbed. And the summation over j epsilon k lambda dot epsilon k lambda prime into e raised to power iota k minus k prime dot rj0 is equal to n multiplied by delta k k prime delta lambda lambda prime. Now, an important condition that we now require that pi and delta ri should be real. So this implies that what requires them to be real is that we now put a constraint, that is p star k lambda is equal to p minus k lambda, and at the same time q star k lambda is equal to q minus k lambda. So the star is basically the complex conjugate. So this implies that, like, if it has to be real, then the complex conjugate should be the same, except that now k has to be replaced by minus k. Also, pk lambda is equal to epsilon hat k lambda into pk lambda. So you can see from here that this vector p is broken up into two parts. One is a vector which is basically the polarization direction, multiplied by a scalar quantity which is p. And exactly in a similar manner, qk lambda is equal to epsilon hat k lambda into qk lambda. That is, you are breaking up this coordinate q, which is a vector quantity, into a vector and a scalar. That is, you are multiplying the polarization vector with a scalar q. And immediately you see that the product becomes actually a vector quantity. Now we initiate the quantization process by replacing the variables exactly in the same manner as before we did for one dimension, pk lambda and qk lambda, by the corresponding quantum mechanical operators pk lambda hat and qk lambda hat, which satisfy the commutation relation, that is pk lambda and qk lambda prime qk prime lambda prime is equal to minus iota h cross delta k k prime into delta lambda lambda prime. And if k is not equal to k prime, and also if lambda is not equal to lambda prime, then on the right hand side you will have. So in either of this case you will have a 0 on the right hand side. As before, we now introduce the creation and annihilation operators a hat dagger k lambda and a hat k lambda, defined as follows. That is, q hat k lambda, which is the position coordinate, is proportional to the a k lambda minus a dagger minus k lambda, and the momentum as proportional to a dagger k lambda plus a minus k lambda. Now, comparing these above results with the earlier one-dimensional results, the operators a dagger k lambda and a k lambda satisfy the following computation relation as before. That is, a k lambda a dagger k prime lambda prime is equal to delta k k prime delta lambda lambda prime. And also very obvious, that is a k lambda a k prime lambda prime, computation of this is also equal to 0, and at the same time if you take the Hermitian conjugate also, then it is still 0. For the three-dimensional case, the displacement of the jth ion and the corresponding momentum is written as delta rj vector is equal to the summation over k lambda square root of h cross divided by 2mn omega k lambda multiplied by the polarization vector epsilon hat k lambda e raised to power iota k dot r j0 multiplied by a k lambda minus a dagger minus k lambda And in a similar manner, the position of the momentum of the corresponding momentum of the jth ion is written as shown, where you see that now if you compare it with the one-dimensional case, here we have an additional factor of the polarization which was not there in the one-dimensional case. And finally, the three-dimensional quantized Hamiltonian now is written in such a manner that is summation over k lambda h cross omega k lambda a k lambda dagger a k lambda plus half. So what is the difference between the three-dimensional quantized Hamiltonian and the one-dimensional quantized Hamiltonian? As you can see that they look similar, but an additional parameter which is appearing here is the polarization lambda. So the difference being that in a three-dimension you have now to introduce the polarization factor of lambda. This parameter lambda is denoting what polarization it is. 0-point energy. So this particular figure actually shows the lowest vibrational state carries energy and is known as the 0-point energy. So if you refer back to the Hamiltonian, which we had discussed earlier in the 1D as well as in the 3D case, is the average of this A dagger A is 0, which basically represents the number of phonons, is 0. You still have some finite energy which is half of summation over h cross omega k lambda. So that is actually the 0-point energy, where as you can see is depicted in this figure n equal to 0, which is half h cross omega. So in the lowest vibrational state, n equal to 0, energy of harmonic oscillator with the mode k is not 0. It has a finite value, half h cross omega k lambda. This is called 0-point energy. And also this figure shows correspondingly that as the energies, as you go from n equal to 0 till 1, 2, 3, all these are equally spaced and the spacing is h cross omega. So students, let us summarize what we have learned in this module. The first thing that we learned was the quantized Hamiltonian obtained during the process of quantization is Hermitian in nature. How we can write the displacement of the jth ion and its corresponding momentum in terms of the quantum mechanical operators. To obtain the eigenvalues from the Hamiltonian of a linear chain of ions. That we have learned is that no phonons are present in the quantum ground state. To obtain the three-dimensional quantized Hamiltonian in terms of annihilation and creation operators, we also learned the energy of the harmonic oscillator is not 0 in the lowest vibrational state. 0-point energy, that is, it is called, and has some value.